Hey there, STEM Chemistry. This is Mystery Arc. This is podcast 7.3, and we're going to actually get into the gas laws and what the gas laws are and what they entail. This is fun. All right, so there are different properties of gas that are described or explained using the gas laws, and those different ones are the amount of gas, and they all relate to pressure. Okay, so the amount of gas, if we increase the number of particles that we have, or moles of gas that we have, we're actually going to increase the pressure. So think, if we've got a container sitting here, all right, and we've got so many molecules or so many particles of gas in here, the pressure will be whatever it is. Okay, 1, 2, 3, 4, 5, 6, 7. Let's say we double the amount of particles that we have. Well, we're going to increase the pressure that's inside of this container here. Okay, it's just the same thing if you have 4 people in an elevator and then you go up a couple floors and you end up picking up, nobody gets off, but you pick up 4 more people. Well, it's cramped in there, right? So the same thing's going on there. All right, well, volume. If you reduce the amount of volume, you're going to tend to increase the pressure as well. So let's say that we take this volume right here, and instead of cutting it in half and letting half of these people go, we're going to make this smaller, and we're going to put the same number of gas molecules in it. Okay, look at that pressure. Look how it increases, right? And then the last one is temperature. If we increase the temperature, we're typically going to increase the pressure. And that's because if you increase temperature, you're increasing kinetic energy. If you increase kinetic energy, you're going to increase the collisions that the gas particles are going to have with each other and with the container. And those collisions are what give you pressure. All right, so one of the laws that we have to look at is called Boyle's Law. They are all named after different scientists. Okay, so Boyle, I believe it was Robert Boyle, but I cannot remember for sure, so don't quote me on that. All right, so he did some work and they came up with this law for him that says that pressure is the result of molecules colliding with the walls of a container. And he says, his law says, that if you have a container and you have particles in it. Okay, so we've got 9, 10. Let's put 10 in here. Okay, in a 4x4 container, pressure is 1 atmosphere. We've got 10 particles. Well, in this next container, which is half the size of it, we're going to have 6, 7, 8, 9, 10. We're going to have 10 in it. So what do you think is after you pressure, and for the volume, if we want to keep this pressure the same at 1 atmosphere, do you think we would be able to have those 10 in there? No. Right? The pressure is going to change. All right, well, what happens here? I don't know why. That's why I stopped for a second, because that's not supposed to be there. Let's fix that. It goes from 1 atmosphere. It does not stay 1 atmosphere. Sorry, guys. That's why I kept stopping. Okay, so we have a smaller volume. It's half the volume. And if it's half the volume with the same number of particles, what's going to happen to the pressure? Well, it should go up by double, right? So if one goes down, one goes up. If one goes up, one goes down, right? Okay, so what happens if we take that same gas and I lost my little... Where's my, oh, it's around here somewhere. Okay, well, anyway, so I take that same gas and I put it into an extremely small container. 6, 7, 8, 9, 10. So what's going to happen to that pressure there? Well, it's going to go up again, right? So at 2 atmosphere, because we've just shrank it in half again, now it's going to be at 4 atmospheres. So it's just going to keep going up by the same proportion that you take the volume down. All right, so as the container, well, I think I have it here. Same number of particles in each box, smaller container equals more collisions, which is going to give us an increase in pressure. All right, so over here on the side, we're going to sketch a graph to show how pressure changes in response to increasing volume. So actually, if we have pressure here and, no, volume should be here and pressure would be here. Okay, so pressure changes to increase. Oh, I'm sorry, guys. I'm messing up again. Pressure here, volume here. It really doesn't matter, actually. As the volume increases, the pressure is going to decrease, and as the volume decreases, the pressure increases. right? So it's an inverse relationship. It's what I call a seesaw relationship, is one goes up, the other goes down. Okay, so this, and you'll end up seeing this a lot, is pressure times volume is equal to K, which is a constant. Okay, so that's going to end up giving us Boyle's law, because we're going to end up setting this K. We'll use the K, and there's a lot of math here, and we can derive it all, but I'm not going to. Okay, and we can actually end up using this to say if we have a change in condition, that the initial pressure times the initial volume would be equal to the final pressure and the final volume. Okay, and so yeah, again, just as the volume increases, the pressure decreases by the same proportion, and vice versa. All right, so let's do a practice problem. It says if we have an initial pressure of 1 atmosphere and an initial volume of 8 milliliters, and then we have a final volume of 10 milliliters, what is the final pressure? All right, so P1 V1 is equal to P2 V2. And all we have to do is plug this in. So 1 ATM times 8 ml, and that's equal to 10 ml, and then that's going to be times P2. Right, now, the only thing that you have to be super careful of with this is you have to make sure that your units cancel out. So you don't ever want to have, if this is milliliters and this is liters, that it can't work. You have to convert. Okay, so this right here would be, and however you want to do it, I would take care of this first, but you can do the math however you want as long as you get the right answer, right? That cancels, this cancels here, and so pressure is going to be equal to atmospheres, ATM, right? And then 1 times 8 divided by 10, so 0.8 atmospheres, and that would be your answer. This is pretty easy, right? Okay, of course it is. Okay, so next law is Charles's law. So in this one, they're talking about the relationship between temperature and volume. And they say as the Kelvin temperature increases, the volume of the gas will increase. So this is what we call a direct proportion. As one goes up, the other goes up. As one goes down, the other goes down. I like to call this the monkey see, monkey do. You see it in the hallways all the time. As somebody does something stupid, somebody else comes behind them and decides to do the same stupid thing, right? There you go. All right, so direct relationship between the two, and this only happens if pressure and temperature remain constant. Okay, so if we double the temperature, we double the volume. If we reduce the temperature by half, we reduce the volume by half. It's a direct proportion, so you have to make sure that if you, whatever you, like if you triple the volume, then you triple the temperature. Okay, so it's a direct proportion. All right, so this is going to give us, in a direct proportion, volume divided by temperature. And since if you increase by 1, you increase the other by 1, so it's actually going to end up giving you a line that looks like this. All right, and to get this, it would be rise over run, which would be volume over temperature, right? All right, so that's going to be equal to a constant. Again, you guys love this constant thing, don't you? All right, so let's see if we could set this up and say, well, what if we have initial and final temperatures and initial and final volumes? Well, we can do the same thing. So V1 over T1, that's a 1, is equal to V2 over T2. Okay, and then we can use this to solve problems, right? All right, so here's a practice problem. A sample of gas occupies 3.5 liters, that's volume 1, at 300 Kelvin, so that's T1. What volume, that's what we're looking for, will it occupy at 200 Kelvin? All right, so V1 over T1 is equal to V2 over T2. We plug this in, 3.5 liters over 300 Kelvin, and that's going to be equal to X or V2 or whatever letter you want to use there over 200 Kelvin, right? How do we solve a proportion? Well, we cross multiply and then we divide, right? So 3.5 liters times 200 Kelvin is equal to 300 Kelvin times X. I would divide both sides by 300 Kelvin. The kelvins cancel, that cancels, we're left with X, which is the same thing as volume 2, and then you just have to do the math in liters. How many significant figures? We want 2 significant figures. But Miss Ruark, the temperature doesn't have two significant figures. It only has one. Okay, well, temperature is what we call an exact number. I told you they'd come back from last semester. Okay, exact numbers do not get used to determine significant figures, so temperature does not get used to determine significant figures. All right, so on this one, you would end up doing the math and you would get two significant figures. I don't have a calculator with me, so I'll let you guys solve it. All right. Practice problem number 3. I want you to try this one on your own. Just remember that you have to change Celsius to Kelvin first. You cannot solve a gas laws problem with Celsius. It doesn't happen. Okay, we also have a couple more laws. We have Gay-Lussac's law, which deals with the relationship between pressure and temperature. It is a direct relationship. So pressure over temperature, P1 over T1 is equal to P2 over T2. And then Avogadro's law deals with the number of moles of a gas, and it says that they will increase if the volume increases, etc., etc. So N1, V1 over N1 is equal to V2 over N2. Okay? It's all the same relationship, right? Okay. So instead of going and remembering every single one of those laws, this is a lot of laws, plus there's more coming. Okay, so instead of doing that, we have this thing called the combined gas law, and it just takes all those laws and throws them all into the same equation. Okay, so we know that pressure, P1, V1, or here, let's do it this way. We have pressure and volume is equal to a constant. We have V over T is equal to a constant. We have V over N is equal to a constant. And we have P over T is equal to a constant. Well, if they're all equal to a constant, why can't we just throw them all together, right? So P times V is the same, and we could put those both over T, right? So P V over T and V over N, so we throw N there, and that's all equal to K. Well, you've got P1 V1 over T1, N1 is equal to P2 V2 over T2, N2. Okay, and this would be your combined gas law. Now, the only time you use this is important, so listen. The only time you use this is if they're changing conditions. So you have to have initial and you have to have final conditions. There has to be a change in order to use this. And I'm stressing that because there's another one coming along that you'll use for other stuff, okay? So make sure you pay attention. All right, practice problem. A gas tank has a volume of 28.1 meters cubed and a pressure of 18.4 atmospheres. The temperature of the gas tank is 32 degrees Celsius. What is the Celsius temperature? That's what we're looking for, T2. When the gas is put in an 11.2 meter cubed tank, that's pressure 2, that's volume 2, with a pressure of 22.7 atmospheres. There's P2. Okay, so we've got P1 V1 over T1 is equal to P2 V2 over T2. I know I had N's in here last time, and sometimes you'll have them and sometimes you won't. If they're not in there, just assume that it remains constant and you don't have to worry about them. Okay, and the nice thing about this is you can derive any of those other ones, because anytime something is held constant, it's not included in the equation. Let me show you. Since N is not included, it's going to be the same on both sides, so we just take it out, right? There you go. All right, so we plug this in. We've got 18.4 atmospheres. And then for V1, we've got 28.1 meters cubed. And then for T1, we've got 32. Well, to get from Celsius to Kelvin, we've got to do 32, and we add, can't remember if we add or subtract. I have to do this every single time. 0 Kelvin plus 2. Okay, so we subtract, because if I've got Kelvin, I have to add 273 to get to degrees Celsius. Okay. All right, so we're going to subtract 273, and that will give us our degrees in Kelvin. Okay, so you're going to do that and plug that in down here. And then you do the same thing on the other side. I'm going to run out of time, so I'm not going to be able to finish this for you. But you can finish it and bring it to class and check it with mine to make sure that you have the right answer. Okay? I'll see you then.